Hello everyone, in this lesson we will speak about ultrasonic sensors. We will learn the theory behind these sensors and how we can integrate these sensors in our embedded systems. Principles. The ultrasonic sensor works on the same principles as a radar system. Ultrasonic sensors emits an ultrasonic wave and receives the wave reflected back from the target. Ultrasounds or ultrasonic waves are sound waves with a higher frequency than the upper audible limit of human hearing. The ultrasounds starts from 20 kHz. What's between 20 Hz and 20 kHz is the audible range for a human being. Sound waves are mechanical vibrations that propagate in a medium, for example, air, water, and so on. An ultrasonic sensor can convert electrical energy into acoustic waves and vice versa. The acoustic wave signal is an ultrasonic wave traveling at a frequency above 20 kHz. The famous HC-SR04 ultrasonic sensor generates ultrasonic waves at 40 kHz frequency. Ultrasonic pulses travel in a cone-shaped beam. The highest intensity is on the axis and decreases with rising angles. Here are some examples of cone-shaped beams. We can have symmetric type beam and asymmetric type beam. The frequency of vibration of the transducer determines the range of an ultrasonic sensor. Short-range ultrasonic sensors use higher frequency, while long-range ultrasonic sensors use lower frequency. All materials which reflect sound can be detected, regardless of their color. Even transparent materials or tin foils represent no problem for an ultrasonic sensor. Polar coordinate system is used to draw the beam pattern of ultrasonic transducer. Blind zone. The blind zone is a unusable area that is closest to the face of the sensor. The sensor cannot accurately receive the echo because the beam completes a detection cycle before the sensor completes its transmission. Example of construction. Piezoelectric crystals are used for sensor elements. Piezoelectric crystals will oscillate at high frequency when electric energy is applied to it. A piezoelectric crystal will generate electrical signal when ultrasound wave hit the sensor surface in reverse. Here's an example of construction of an ultrasonic sensor. We have the case, we have the metal plate with a horn on top of it, and we have the piezoelectric crystal, to which we have two electrical connections. In this picture, we see the representation of the direct piezoelectric effect and the converse piezoelectric effect. Applications of ultrasonic sensors. Some of the applications can be distance measurement, level measurement, obstacle detection, counting, fluid flow, medical imaging, and others. HC-SR04 specification. The working voltage is of 5 volts DC. The no-load current is somewhere around 2 milliamperes. Working current 15 milliamperes. And the working frequency is of 40 kHz. Other important notes is the measuring angle, which is 30 degrees, the range of 4 meters, the minimum range of 2 centimeters, resolution, and the trigger input pulse width must be of at least 10 microseconds. How this sensor works? The sensor consists of a transmitter, here, that generates ultrasonic waves, a receiver that perceives the echo, here, the pinout. We have the VCC pin, which is the power supply for the sensor. We have the trigger pin, which is used to trigger the ultrasonic sound pulses. We have the echo pin, which produces a pulse when the reflected signal is received. And we have the ground pin. A pulse of at least 10 microseconds is applied to trigger pin. So this is the pulse. And in response, the sensor transmits a burst of 8 pulses at 40 kHz. So here is the burst of pulses. The 8 pulses represents also the signature of the sensor, allowing the receiver to differentiate between the transmitted pattern and ambient ultrasounds. At the end of the burst, the echo pin goes high and awaits the reflection of pulses. So here the echo pin goes high, and when the reflecting signal is received, the echo pin goes low. So here is the transmitter that transmits the ultrasonic wave, and the object will reflect the signal, and the receiver will receive these 8 pulses as the signature, and it will make the echo pin go low. In case the pulses are not reflected back, then the echo signal will enter in timeout after 38 milliseconds and return low, which means no object was found by the beam in the range of the sensor. If the pulses are reflected back, the echo pin goes low as soon as the signal is received. This produces a pulse whose width is equal to the time it took for the signal to be received. The width of the received pulse is then used to calculate the distance to the reflected object as following. Distance equal to the speed of sound in the medium times the time that we get from here divided by 2. We divide by 2 because width of the pulse indicates the time it took for the signal to be sent out and reflected back. If you want to be more precise with speed of sound traversing the air, you can use the following formula. Now let's look at a practical example of HC-SR04 sensor. For the practical example, we will use the Nucleo board, and to configure the Nucleo board, we will use the STM32 CubeMX. Let's start a new project. How to install this software, I have a previous video on my channel, you can go watch that. Now we need to select the board. Type here Nucleo. I have this board, so I will select this, double click on it. It will ask me if I want to initialize all peripherals with their default mode. I press yes. This will initialize the UART, the LED that's on the board, the push button here. Also it will initialize the external clock, but we don't have that on the board. Let's disable that. Go to the RCC. And we disable the high speed external clock. Let's go to the clock configuration. Now we see that we use the HSI, which stands for high speed internal clock. It goes to a phase locked loop configuration, and it will multiply the clock. We will have a 84 MHz clock for board. Now let's open the datasheet. And inside the datasheet, you want to search for block diagram. So here's the block diagram. We know that we need 2 timers, one to make the echo capture and the other one to make the microseconds delay. So we will use this 32-bit timer for the echo capture and the timer 3 for the microsecond delay. Both of the timers are connected to this bus, so APB1, Advanced Peripheral Bus. There is also another one, AHB, which stands for Advanced High Performance Bus. This one is much faster than peripheral one. Also there is an APB2, but we need this APB1 to be configured. So let's see what clock is on APB1. We also have 84 MHz. Let's give a name to the project. Application structure, we leave it as default. Here we will use the STM32 Cube ID. We keep this as default. Okay, so let's go back to the pinout and configuration, and let's configure the two timers. For that, we go to the timers. We want to use timer 2. To use the timer, you need to select a clock source. We will select the internal clock. Now that we have selected the internal clock, we need to select channel to be input capture direct mode. Go right here, the prescaler. Because the clock is at 84 MHz, we want the prescaler to be 1 MHz. For that, we put 84 minus 1. Counter mode, okay, to start with up counting. Let's put a period in here. We can change here between decimal and hexadecimal. I'll put the maximum period. Press enter. For the channel configuration, we want to see the both edges. IC selection direct, no division. Let's put a filter. This is a low pass filter. Let's put a 5 value in here. And that's it. Timer 2 was configured, and automatically it also appeared inside the pinout view. So is the pin PA0. For this, we need to go to the STM32 Nucleo boards user manual, go to the extension connectors, search for our board. Once we find it, we can see the PA0. It's connected to this pin and also this. So this is the Arduino pinout and this is the ST Morpho pinout. So either we use this 1 or this 28. This will be PA0 pin. Now let's configure the timer that will be used for the microsecond delay. I will configure timer 3. To enable it, we only need to set the clock source. For this timer, we don't need any channel, but we need the prescalers. So let's rename the timer 2 to be more explicit. We can right click, enter the user label. Maybe it's better like this. Let's select another pin that will be the trigger pin. For that, I want to use this PA8. Go back to the CubeMX. Here's the PA8. Click on it. We need it as GPIO output because we will set the trigger pin high for 10 microseconds. Right click on it, enter user label. This will be trigger pin. We don't need the push button for this project, so click on it and put it in the reset state. Also, we can do this for the external oscillator. So before we generate the code, let's go back to the timer 2 and go to the interrupt table, enable the interrupt. Everything looks fine. Now let's save the project. Project will be saved to the location that you specified here. Now press the button to generate the code. The code generation is complete. Press the open project. STM32 Cube ID will automatically be opened. So let's see what we have. Inside the SRC folder, we have the main source file, where the main function will be called. Now let's begin the code walkthrough. We have this private type def under the user code begin PTD, which stands for private type def. This type def is an enumeration with 3 values inside. The name of the enumeration is ages_e. Then we have the private defines also between the user labels. These defines are used to remove magic numbers inside the code, so it will be more clearer when the code is read to see that a echo capture reset is happening or a echo capture complete was happening. We have a define for our timer in case you will want to use another timer for the microsecond delay. You need to change here the timer number. We have a project variant to use floats or not to use floats, and we have a buffer size of 100 characters. Next, we have the private variables. So we have some globals that we will see inside the code. Inside the main function, we only added code after the label user code begin number 3. Be sure to be after this label and not between here, because if you have code between here, when you press generate code again, that code will be lost. If you want to put some local variables for the main function, you need to put them here in the begin section 1. If you have some initialization of some drivers that are not from STM32 CubeMX, you need to put them here, and so on. Also, we have a section 2 where you can put something, and the infinite while loop, you can put code before the while begins, just before it starts, or at the end of the while. You also can put the code right here. In the user section number 4, we have added the delay in microseconds. This is according to a video from this guy. We will talk about this configuration of the timers in a future lesson, where we will talk about all the peripherals of a microcontroller, and we will give example of this STM32. Next function that is defined by us is a capture callback that will be called when the interrupt happens, and the interrupt will happen on the rising edge and the falling edge, as we configure to the timer 2. We have said here the input capture, the polarity selection is on both edges, so it will trigger an interrupt. And that interrupt will call this callback, and inside here we will toggle the LED pin to see when the capture is happening. Inside the interrupt, we will verify if the edge direction is the rising edge, and if it's the rising edge, we will store the value of the timer inside the rising edge counter, and we will set the edge direction to the falling edge. So this will be the next direction. And when the echo pin goes low, the second call of the interrupt will be called on the falling edge, and the edge direction will be falling edge, and we will store the falling edge counter value read from the timer to this variable. Then we set the next edge direction to the rising edge, in case another read will be triggered. What else we will do? We'll say that the echo capture flag is complete using this macro instruction to remove the magic number, as I said before, and this global variable. And now here is the magic that will read the sensor. So this is the function that is called inside the while loop. What it does: first, it sets the trigger pin to low for a short time. This is to be sure that it's low, in case it wasn't. It delays here 3 microseconds using this function that uses the timer 3. So that function uses this timer 3. After that, the trigger pin will be set to high for 10 microseconds, and after that it will be set back to low. What this will do? So it will do this thing right here. It will set for 10 microseconds the trigger pin to high, and this will result in a burst of pulses. After the burst is sent, then the echo signal is measured. So we start the timer and we will wait for the EC flag to come. We also start in parallel how shall I say, a timeout that will get the ticks of the system in milliseconds, and in case this tick goes over 500 milliseconds, then the function will not be blocked here. So this do while is for protection. In case the echo capture is complete, this if will be true, and we will break outside the do while and set the echo capture flag back to reset state and stop the timer. After we have the falling edge counter value and the rising edge counter value from the interrupts, we verify that the falling edge counter is greater than the rising edge, and if true, we get the distance. How we get a distance? Using the formula. So this is the formula. This part right here is the t, which represents the time, and this part right here is the speed of sound in air, and this speed of sound in air was already divided by 2 to have these 2 from here. So let's navigate back to our function. If the falling edge is below rising edge, then the distance will be 0. Next, we prepare the string that will be sent over the UART. So inside the buffer, with the printf function, we will put the characters of this string. So distance equal to the value in floating with 1 decimal point, centimeters, and I also put the counters to see at which value they are. And after the buffer is completed, we send it over the UART using the STM32 call UART transmit function from library. So this is it. This is the program. Now let's build it. everything built successfully. So now let's flash the code to the board to see what's happening. First, let's go to the device manager, go to the COM ports, and see the COM port of the board. Then go to the PuTTY, serial, configure the speed. So the speed is configured inside CubeMX. If you go to the connectivity and UART2, you will find here the baud rate. So the baud rate is 115-200. 115-200. We forgot to insert the COM, but let's flash the program first. Connect to the target. Now let's go to the target, program, go to the project, to the debug, and find the bin file. Open it, press start to flash it. So the flashing is complete. Now let's open again the PuTTY. I already have it here. I can press load. So COM3 115-200. If you made the settings, you can give it a name and press save. So next time you will also have in the list. Now let's press open. From the left side until the right side, the size of the file is 21 centimeters. So let's put something in front of the file and see the reading. The reading is 21.2 centimeters. If I come closer, let's say to the half, so the reading is somewhere accurate. Now let's see the option without the floating number. For this, we must go inside the project, comment out this define, and build again the project. The project has built. Go to the target, program, browse for the file, press open, press start, go to PuTTY terminal. So now we have the distance without the floating point number. Let's see again the size of the file. It's 21 centimeters. To the half, 10 centimeters. Let's go 11 in here. Okay. So I can say that the integer and the floating point calculation are correct. Here is one of the limitation for this sensor. I have here a plush toy. So if I put this right here, let's put it like this. Now the reading is not correct anymore. HC-SR04 limitations. The distance between the sensor and the object obstacle is more than 4 meters. The object has its reflective surface at a shallow angle so that ultrasound will not be reflected back towards the sensor. The object is too small to reflect enough sound back to the sensor. Improper mount of the sensor on the system. Soft objects and objects with irregular surfaces, such as carpets, stuffed animals, or plush toys, absorb rather than reflect the ultrasound wave. We have seen this limitation in the practical example. To overcome some of the limitations, we can install multiple sensors on the system, or we can combine with other type of sensors. If you enjoyed this video, don't forget to like it and subscribe to my channel for future videos.